Picture this scenario for a second. A major bank rolls out a brand new, highly capable AI assistant. And they've done everything right, or so they think, carefully fine-tuning it on their internal data. They feed it proprietary credit scoring models, highly confidential operational procedures, and years of historical client data, just so it can, truly understand the business. Fast forward 6 months. A brand new junior sales rep types a completely standard, totally harmless question into the prompt. The AI responds. But woven right into the middle of its super helpful answer are incredibly precise, highly confidential financial details about a specific historical client. Details this novice employee absolutely did not have the clearance to see. The model had just flat out memorized its training data and casually handed it over. Well, welcome to our explainer on AI memory risks and the Minerva Protocol. Today, we're diving into a fascinating and frankly kind of terrifying reality of enterprise AI deployments. Here's our roadmap for today. 1. Le piège de la mémorisation. 2. LoRA, l'amplificateur des risques. 3. RAGAZ et failles mémoire. 4. L'émergence des fuites agentiques. 5. Le protocole Minerva. And 6. Conformité et gouvernance IA. Let's jump right into section 1. Le piège de la mémorisation, the science behind AI memory. Okay, so if we actually want to secure these systems, we first have to understand the science behind why large language models act like they have a photographic memory in the first place. To get a handle on this, we have to look back at some foundational 2021 research by Carlini and his team. They proved something that completely turned AI privacy on its head. They demonstrated that models like GPT-2 could literally be prompted to spit out exact, verbatim training data. We're talking personal emails, phone numbers, physical addresses, and the most crucial takeaway here, this regurgitation isn't some weird glitch in the code. No, it is a fundamental inherent feature of how these models are trained. Basically, the more frequently a piece of data appears in the training set, and the larger the model, the more likely it is to be memorized. Moving on to section 2. LoRA, l'amplificateur des risques, the enterprise vulnerability. Now, let's talk about why AI models memorize so aggressively during fine-tuning, specifically looking at everyone's favorite enterprise tool, LoRA. Low-rank adaptation has basically become the gold standard for customizing models, right? But it actually multiplies this exact privacy threat. Look at this comparison. On the left, you've got your massive base model, like a Llama 3 70B, sitting at around 140 gigabytes. On the right, you have a highly compressed LoRA adapter, which is only, 2 to 8 gigabytes? Now, enterprises absolutely love LoRA because it's lightweight and you can train it on a standard GPU in a matter of hours. But here is the massive risk for enterprises. When you pack highly repetitive, incredibly sensitive internal data, think proprietary procedures or client medical records, into that tiny 2 to 8 gigabyte space, you're practically guaranteeing concentrated memorization. The sheer density of the fine-tuning data squeezed into such a small adapter essentially forces the model to memorize specifics, meaning your customized LoRA adapter inadvertently becomes a highly concentrated vault of your most sensitive corporate secrets. And hey, before you think, oh, we'll just use a smaller distilled model to solve this, we really need to talk about knowledge distillation. This is a process where a smaller student model is trained to mimic a much larger teacher model. It creates a total illusion of control. You might be sitting there thinking, well, the student model never directly saw the confidential training documents, so we're safe. Actually, scratch that. Research shows the student unintentionally inherits the teacher's memorized data anyway. If that massive teacher model memorized a sensitive secret, the smaller student can absolutely still leak it, even though it never directly read the original file. Which brings us to Section 3, Ragged and Fails Memory, the false sense of security. So the bottom line is that baking sensitive data directly into the model's weights is incredibly risky. And this is exactly why so many enterprise IT leaders tell me that RAG, Retrieval Augmented Generation, is inherently secure. But let's break down why assuming RAG is a silver bullet is actually pretty dangerous. Yes, RAG keeps your documents out of the model's permanent weights, for sure. But consider the actual pipeline for a second. When a user asks a question, your system pulls confidential document chunks and injects them directly into the prompt in clear text. The LLM then processes this sensitive data during inference, loading it straight into the system's KV cache. And here's the kicker. Even after the user closes the session, that confidential chunk leaves volatile memory residues behind in the system. It's literally like leaving a highly classified document face up on a shared office photocopier. You haven't eliminated the memory risk at all. You've just moved it from the model's permanent weights over to the system's temporary memory. Oh, and to add a really surprising fact to this, those databases holding your RAG documents, yeah, they aren't totally safe either. We often think of the vector databases used in RAG as just storing these abstract mathematical representations, or embeddings of text. But 2023 research by Morris and his colleagues show that these embeddings can actually be partially reconstructed through what's called inversion attacks. Hackers can literally reverse engineer the abstract math inside your vector databases to expose the confidential original texts. So an unauthorized access to your vector store isn't just an exposure of random numbers, it's an exposure of your actual literal secrets.
Let's look ahead in Section 4. L'émergence des fuites agentiques, autonomous exfiltration.
Fast forward to late 2025 and 2026, and how to avoid the exfiltration nightmares we're gonna see. This builds into an even more severe vulnerability when we start talking about autonomous AI agents. This plays out exactly like a digital heist. So, why do AI agents leak? Because unlike a simple chatbot, an autonomous agent has to maintain a really dense, long-running context memory that can last for hours as it completes a complex task. It's pulling from databases, reading histories, and holding all of that in active memory. That's step 1. Step 2, a bad actor slips in a malicious prompt injection. Step 3 is where the heist actually happens. The attacker tricks the agent into using its own legitimate tools, like sending an email or making a standard API call, to quietly exfiltrate that massive sensitive context memory straight to an external server. The agent is leaking data using the exact permissions you gave it, making these long-running contexts a massive vulnerability. Section 5. Le Protocol Minerva, the diagnostic solution. So, with all these vulnerabilities piling up, from concentrated LoRA memorization to RAG residues and those agentic leaks, we have a major problem on our hands. If we can't crack open a black box model and perform an invasive biopsy on its billions of weights to see what it knows, how on earth do we diagnose the patient? Well, this number right here is the answer: 35. We use the Minerva Protocol. Instead of trying to read the unreadable weights of the model, Minerva relies on 35 distinct behavioral forensic probes. It treats the AI exactly like a medical patient, testing its reflexes and behavioral symptoms through standard API inputs. We stimulate the model and analyze its outputs to mathematically prove if it's harboring memorized data, all without ever touching the underlying architecture. And the way those 35 probes function is incredibly comprehensive. They evaluate the model's variance score across 7 incredibly strict GDPR categories. Everything from identity and financial data, all the way to health, biometric, and even political opinions. By comparing the model's answers against what a statistically normal, non-memorizing model would say, Minerva can spot the exact statistical anomalies that indicate concentrated memorization of highly sensitive data. This rigorous behavioral testing is exactly how you map vulnerabilities in advance and avoid those catastrophic 2026 agentic exfiltration scenarios we just talked about.
Finally, Section 6, Conformité and Gouvernance AI, Securing the Enterprise.
This brilliantly illustrates how we turn all that complex academic diagnostics into crystal clear, actionable governance for your organization. Because at the end of the day, you just need to know if you can safely deploy these systems, right? Minerva provides this exact, concrete framework for compliance officers. It boils all the behavioral science down into 3 simple verdicts. If it reads Minerva_not detected, no significant memorization was found, and you have a documented go for deployment. If it reads Minerva_exposed, the probes found abnormal memorization. That is a strict no-go requiring immediate investigation before you even think about deploying into sensitive zones. And pending simply means the API is paused. It's binary, it's clear, and it completely removes the guesswork from enterprise deployment. And look, this isn't just about internal peace of mind. It's about strict legal compliance. Article 10 of the AI Act mandates that providers of high-risk AI systems have documented governance to verify training data integrity and identify biases. Having a documented Minerva not detected report acts as the exact behavioral due diligence required by Article 10. It is literally the paper trail proving you rigorously tested the model's memory before putting it into production. Which brings us to the final critical question you really have to ask yourself after reviewing this explainer. Look at your own internal deployments. Look at your fine-tuned LoRA adapters and your RAG pipelines right now. Could your current enterprise AI deployment actually pass an Article 10 behavioral audit today? It's a provocative thought, I know, but as we've seen, just hoping your AI hasn't memorized your deepest corporate secrets is no longer a viable strategy. Thanks so much for joining me to explore the realities of AI memory, and I highly, highly recommend evaluating your own system's reflexes before a junior employee or worse, an autonomous agent does it for you.